Ever since people started looking up at the stars, we've wondered about how things really work. The night sky, with its countless stars and mysterious Milky Way, has always sparked our curiosity. What lies beyond those twinkling lights? What forces govern the cosmos? What's the universe made of? Is it just stars and galaxies, or is there something more? As we peer deeper into space with powerful telescopes like Hubble, we uncover more questions than answers. What rules does it follow? Are there universal laws that everything abides by? These cosmic rules, often invisible to the naked eye, dictate the behavior of everything from the smallest particles to the largest galaxies. For a long time, these questions were just for philosophers and religious thinkers. Ancient civilizations built observatories and created intricate drawings to understand the heavens. They pondered the nature of existence and the workings of the universe. But then, modern science came along and we started to figure out ways to really investigate these mysteries. With the advent of the scientific method, we began to test our theories and make groundbreaking discoveries. Physics, especially, has made huge progress in uncovering the universe's secrets. From the tiniest particles in particle colliders to the vast simulations of the universe, physicists have been at the forefront of this quest. Right now, our understanding of the universe depends on two big ideas: general relativity and quantum mechanics. General relativity, proposed by Einstein, explains the force of gravity and the large-scale structure of the universe. Quantum mechanics, on the other hand, deals with the behavior of particles at the smallest scales. These two theories, while both super successful in their own areas, describe the world in very different ways. General relativity works well for stars and galaxies, while quantum mechanics excels at explaining atoms and subatomic particles. But they don't always agree with each other. This difference has confused physicists for decades, leading to a search for a single, big theory, one that can combine these seemingly opposite views. The quest for a unified theory, often called the theory of everything, aims to bridge the gap between these two pillars of modern physics. This is where string theory comes in. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. String theory suggests that the smallest bits of the universe aren't tiny points, but tiny little strings. These strings can vibrate at different frequencies, and their vibrations determine the properties of particles. These strings vibrate in different ways, kind of like the strings on a violin, and that's what makes all the different particles and forces in our universe. By understanding these vibrations, we hope to unlock the secrets of the cosmos and finally achieve a unified theory. To understand why string theory is important, we need to delve into the foundations of our current understanding of the universe. Our current physics ideas, while incredibly powerful, have limitations that become apparent under certain extreme conditions. Our understanding of the universe is built on two groundbreaking theories: general relativity and quantum mechanics. General relativity, formulated by Albert Einstein, provides a comprehensive description of gravity. It explains the motion of planets, stars, and galaxies, and predicts phenomena such as black holes and gravitational waves with remarkable accuracy. On the other hand, quantum mechanics focuses on the behavior of atoms and subatomic particles, providing insights into the nature of light and matter at the smallest scales. However, these two theories clash when applied to extreme conditions, such as the very early universe or the center of a black hole. General relativity envisions gravity as a smooth curvature in space-time, while quantum mechanics describes the universe as composed of discrete, unpredictable particles. String theory aims to bridge this gap by offering a framework that unifies gravity and quantum mechanics. By proposing that everything in the universe is made up of tiny, vibrating strings, string theory provides a revolutionary perspective on the nature of reality, potentially solving the inconsistencies between general relativity and quantum mechanics. This new approach not only offers a way to reconcile the two pillars of modern physics, but also opens up new avenues for understanding the fundamental structure of the universe. String theory could be the key to unlocking the mysteries that have puzzled scientists for decades, providing a deeper, more unified understanding of the cosmos. Think about a violin string. When you pluck it, it vibrates, creating a beautiful sound that resonates in the air. The vibration of the string produces waves, and these waves are what we hear as music. The different ways it vibrates make different musical notes, each with its own unique frequency and tone. Now imagine that string is super tiny, way smaller than an atom. Imagine it vibrating at a scale so small, it's almost unimaginable. Imagine there are also more dimensions than the three we see, and the one-time dimension we experience every day. These extra dimensions are hidden from our everyday experience. That's the basic idea of string theory. It's a revolutionary concept in physics that aims to explain the fundamental nature of the universe. String theory says the smallest parts of the universe aren't points, but these tiny, vibrating strings. These strings are the building blocks of everything. The different vibrations make the different particles and forces we see. Each type of vibration corresponds to a different particle, like electrons, quarks, and photons. Just like a violin string can make lots of different notes, a single string can make a whole bunch of particles depending on how it vibrates. This is how the universe's diversity of particles and forces comes to be. This neat idea tries to bring all the forces of nature, including gravity, together into one theory. It's an elegant solution that could unify our understanding of the cosmos. How can these tiny strings make all the different particles and forces we see? The answer is in the huge number of ways they can vibrate. Think about a guitar string. If you pluck it harder, it vibrates faster and makes a higher note. In string theory, a string with more energy vibrates faster, but energy isn't the only thing that matters. The string's shape and where it is in space also affect how it vibrates. This is where extra dimensions come in. String theory needs extra dimensions beyond the three we see every day. These extra dimensions give the string space to vibrate in tons of ways, making all the particles and forces we see. Extra dimensions are one of the strangest parts of string theory. We're used to three dimensions: length, width, and height and time. But string theory says there are more, maybe 6 or 7 more, that are curled up and hidden. Imagine a garden hose from far away. It looks like a line, one dimension. But if you were an ant on the hose, you'd see it as a surface, 2 dimensions. The other dimension is curled up and hidden from far away. String theory's extra dimensions are curled up super small, too small to see. These hidden dimensions are really important to string theory. String theory affects more than just particle physics. If it's right, the universe is much weirder than we thought. Extra dimensions could mean parallel universes, other 3D universes hidden within the higher dimensions. These parallel universes might have different physics, making a huge, diverse multiverse. The multiverse idea, though still a guess, makes us rethink our place in the cosmos. String theory also suggests everything in the universe is connected. Even though it's elegant and promising, string theory is still controversial. One big criticism is that we can't test it. String theory deals with energies way too high for our current technology, so it's hard to do experiments to see if it's right. Critics say that without evidence, string theory is just math, a nice idea but maybe not real. String theory also has internal problems. It has many possible solutions, each a different possible universe with different laws. This makes us wonder why our universe has the specific laws it does. Despite the problems, the dream of a theory of everything is still exciting. Finding one set of equations to describe everything has been a goal of physics for ages. String theory, with its potential to combine gravity and quantum mechanics, gives us a peek at what such a theory could look like. A unified theory would change how we understand the universe and our place in it. It could answer big questions about the universe's beginning, how it changes, and how it might end. The universe is huge and full of mysteries. As we learn more, we find new questions and challenges. String theory, even if it's just a guess, gives us an interesting way to understand the universe at its most basic level. Right or wrong, it has inspired physicists and changed how we think about the cosmos. The search for a theory of everything continues to push physics forward. We may not have all the answers yet, but the journey itself shows how curious we are and how much we want to learn.